Okay, now we'll go to this 12th session, which is going to be talking about determinant of a matrix. So we'll be talking about what determinant means in definition and talk about how we use this and how we actually calculate this. All right? Oh, let me just erase this. Okay, let's move on. We'll start with some introduction. So basically, what is a determinant? It's very simple. Determinant basically provides like a scalar value associated with square matrices. So what does that mean is that for any sort of square matrix you can have, so if you have some sort of a m by n matrix, let's put it like a little bit here. Okay, whenever you have an m by n matrix, let's say that's A. This always has some sort of scalar value called determinant of A. All right? So what does this mean, really? And actually, like, determinant originated in the study of system of linear equations. That's why we're going to learn about them, and it's very related to solving some linear equations. So, and it's very, very vital in various economic applications also, especially in system representing economic models. For example, you'll be using some sort of determinant to solve some kind of questions, especially, for example, if you're solving whether a solution like yx is y, as a solution, what you would do is that if the A has determinant and A's determinant is not 0, you can actually this actually means that A is invertible. So you can multiply A inverse on both sides, and you can kind of get the unit value for the value x, right? Which is the one you are really one that you want to know about. So something like this, although it's not like the only sole purpose of using determinant, but still, it's one of the examples. All right, let's go. So what sort of properties does determinant have? And we'll know about this soon enough, is that it has a linearity in rows and columns. So what does that mean? It's very simple, actually. And it's related to the other second and third questions where it talks about swapping two rows or columns, which changes the sign. So basically, for example, let me just tell you how to like calculate determinant in 2 by 2 matrices because it's more simple. So suppose that you have a case where you have a 2 by 2 matrix with A, B, C, D in the value. And you want to calculate, let's say this is A. And you want to calculate the determinant of A. Like this. Then what you do is that by definition, you calculate the determinant by doing this. AD minus BC. So what you can kind of see is that basically what we do is that we multiply diagonally and then subtract them. For example, we have AD here, right? Going to here. And then we have the BC here on another diagonal. And we put it here. And then we do subtraction, right? So that's how you do it, okay? Very simple. And you think about it. Think about if you swap these two rows or columns. For example, if you swap the columns, what you're going to get here is that actually swap two columns, you're going to get BD, right? BD and AC. Okay? Think about it for a minute, like what's the determinant for this form, for this matrices? I'll give you some time, okay? So I assume that you did it. So what you get is, you do the diagonal stuff again. You get BC, and you get AD, right? So you do this. And you can kind of realize this is actually same as the one we did before, except that we just changed the sign, right? If you do minus of this, you get the thing in the bottom, right? So basically, if you swatch the columns, it only changes the sign of the values. Similarly, suppose we change the row columns. Not row columns, I'm sorry. Suppose we change the row instead of columns. So. Then we will get something like this, right? Okay, now also think about a minute to figure out what's the answer going to be for the determinant. Interestingly, also, if you solve this, you get diagonal, diagonal, we get BC minus AD. Again, you see that even if you switch the columns, even if you switch the rows, what you get is also just the same value, except the sign is reversed. So basically, what this means is that if you swap two rows, or if you swap two columns, it only changes the sign. And this doesn't only hold for 2x2 matrices. Actually, you can do determinant for all sort of square matrices. And in all those cases, if you swap the rows, two rows, or swap two columns, it just changes the sign, okay? So very interesting property of a determinant. And the third one is more interesting also, is that multiplying a row or column by a scalar multiplies the determinant by the scalar. Interesting, right? So what does it mean is that now, instead of swapping the rows or columns, you just multiply one row or column with some variable. For example, suppose, let's say, the same, except we multiply the first column by 4, okay? So we get this, 4a, 4b. So what's the value for this determinant? Anyone can guess? Interestingly, if you calculate this, what you get is diagonal, diagonal, right? What you get is 4AD minus 4BC. And you can see what this is. If you factor out 4, you get AD minus BC. So basically, it's the former determinant value multiplied by 4. So if you just multiply one row, the result is that you multiply the whole value of the determinant, right, by that scalar. And you can kind of already assume, you can kind of figure out that the answer is going to be also similar if you multiply a row instead of a column. Like, instead of doing here, let's say I did it. Let's say I did row, right, like this. So what you're going to get is diagonal 4AD minus 4BC. See? You get the same result, all right? So basically, multiplying a row by a scalar multiplies the determinant by the scalar. The very interesting property of a determinant is that even if you swap the rows or multiply one row or column, it doesn't change the value severely from the original result, okay? So, and we have another quality which is more interesting, which is number 4, which says, adding a multiple of one row to another leaves the determinant unchanged. So what does that mean? Okay, so let's see. So basically what this tells us is that, for example, suppose that, how we did Gaussian elimination, we used to like multiply one row and just add it to another, right? Similarly, suppose that for AB, I multiply them by 2, so I'm going to get 2A, 2B, right? And I'm going to add this here onto the second row. So I get 2A plus C and 2B plus D, right? So basically what I did was I multiplied the first row by 2 and added them up to the second row. So what's the determinant of this? Very interestingly, what you're going to get is actually like this. So do it diagonal again. So it's a bit more complicated than before ones. D minus 2AB minus BC, right? And this, you can get this together. Oh, sorry. Wait a minute. Oh, no. Sorry. And you can see that this is gone. They subtract each other. And what we're left with is AD minus BC. So, interestingly, we get the same result. So basically what it tells us is that for determinant, if you multiply, or if you add a multiple of one row to another, that leaves the determinant unchanged. The determinant value is not going to change even if you just multiply some one row and just add it to another row, okay? So that's like the very interesting properties of determinants. Okay, so computing determinants. So I already said this, but let me just briefly talk more about it. So basically what we're doing was that we're computing the determinants for 2x2 matrices, because 2x2 matrices are the most easiest form of square matrix that you can do to do multiplication of and try to find a determinant. So if you're given the matrix 2x2, so the determinant of this is going to be defined as DTA, which is written in the slide. We denote determinant of the matrix A as DTA, okay? We call it like determinant of A. So determinant of A is going to be AD minus BC. So basically we multiply the values by diagonally and then we subtract them. Okay, let's resume. Sorry for just interrupting it. Okay. So we're going to give an example of how to calculate determinant, which actually I kind of already did, but I just wrote it in the slide to make it more clear, okay? All right. Okay. For example, we have a 3, 4, 2, 1 matrix, and we are supposed to calculate the determinant of it. And because we already talked about the determinant for 2x2 matrix is done by multiplying the values by diagonally and then subtracting them. We just need to do that, right? So basically, we have 3, 4, 2, 1. So we first multiply diagonal part. So we multiply 3, 1. And we also multiply 4 and 2 and then subtract them. So by doing that, we get minus 5, right? So minus 5 is going to be the determinant of this 2x2 matrices. And that's just how you do it, basically. And the question comes out is that there's a problem where basically there's more than one sort of matrices, right? Especially square matrices, there are 3x3 matrices and 4x4 matrices. So it's going to get a bit more hard to calculate this because, for example, how are we going to calculate the determinant for 3x3 matrices, right? So in this case, we have A, B, C, D, F, G, H, I, like this. In this way, what's the way to calculate the determinant? You can kind of see that I'm not giving you like the rigorous definition of how to calculate the determinant. It's because, I mean, I can tell you what's written in the textbook, but I think that's something you can already find. And usually you don't really use the general definition of matrices. I mean, determine to find out what the determinant of the values are in the matrix. So I'm just going to talk about some practical ways to calculate determinant for some 2 and 3x3 matrices, because I'm pretty sure the ones the determinant you have to find really by your hand in hand are usually going to be only just 2x2 or 3x3 matrices. And if the matrix becomes 4x4, just consult your computers and let it calculate the determinant for you, okay? All right, so In the 3 by 3 matrices, it becomes a little bit harder to calculate determinant. I wrote down the formula here, which is actually called cofactor expansion. So let me explain about what cofactor expansion is, okay? So basically what cofactor expansion is like a way, like a little bit more easier way to calculate the determinant, okay? And the way you do it is as follows. So I wrote down the formula, but you might not know what's happening, so I'll just tell you why. So basically, for this case, we're doing cofactor expansion along the top row. That is, we can actually do it on different rows. For example, for this cofactor expansion to find determinant, we can, instead of just doing like, in this one, the cofactor expansion, we did it by focusing on the top row, right? I'll tell you how we do this. But actually, you can use other rows and columns. Actually, you can start from here, like the first column, or third column, or third row, something like this, okay? But for now, we'll just focus on doing it on top row for simplicity, okay? Let me just write it again. So we have A, B, C, F, G, F. All right. So basically we have this, and we're going to start on the top row. So we'll focus on the ABC row, right? So what you do is that you focus on one point in one points in each top row, and then we do determinant of 2 by 2 matrices on diagonal side. So what does that mean? For example, you see the first equation, you have this, right? And you can kind of see what's happening here is that basically what you did was you start with A, and you exclude this part, the first column part, and just do 2 by 2 determinant here, which is EI minus FH, and then you multiply this 2 by 2 determinant by A, okay? So that's how you got the first term. And for the second term, now you focus on the second point, which is B, right? So B is here. And now you take out the second column. So you assume that EH is not here. And you're doing 2 by 2 determinant for DFGI, okay? So basically you're assuming that the middle column is not there, and you're doing a 2 by 2 matrices for D, F, and G, I. All right? So that's why you get the third term, where you have a B times, where is it? DI minus FG, right? See? And then you just subtract it, okay? Subtract them. And finally, for the last term, it kind of seems obvious now. You focus on C, okay? And you assume that the third column is not there, and you're doing 2 by 2 matrices for the DEGH, right? So basically, now you're doing DEGH determinant. And what you get is you multiply C and you get DH minus EG, and this time you add it. So by doing this, this is same as getting the determinant of the matrix A, okay? But more interesting thing is actually, you don't need to start with the top row actually. You can start with any kind of row and column. So I'll give you an example. So basically, instead of starting from top row, we'll start from, let's make it a bit complicated by starting from, let's start from the third column now. And we do things very similar, okay? So basically, we start from C, right? So we start from C, then similarly, we don't think about the first row and do determinant for this part, and you only get C times D times H, sorry. Right? D times H minus E times G. And you can kind of see this part was actually on the slide when we're doing it on the C right here. I don't think you can see it, but it's basically the same thing. Now, for the second part, we start from F. We don't think about the first, we don't think about the second row now, and think about only A, B, and GH, and do the same thing, but now do minus, subtract them. We get F and we have, what is it, AH, right? AH minus BG. And you can kind of see that, actually we'll do the first, do for the I too, okay? And then we'll tell you, okay? For I, you take out the third row, and again do this, but now you have to, you don't need to add them, not subtract them. And what you get is, you get A, all right, AE minus BD, right? So like this. So what you can see here, interestingly, the C part is basically the same as the third term we did before with the top row. And now the thing about the first term and the second term, you can see that actually AEI is right here, right? You can see in the first row we did, in the slide, we did A times EI minus FH, and the AEI was there. Now AEI is here. So, and for the minus IBD, it's actually also here because in the second term there was minus B times DI, which is same as minus IBD, right? So that's there as well. So this is okay. And for AFH, we also had that minus AFH, which was in the first term of our slide, which had A times minus FH, so it's also there. And also for minus BG times F, which is FBG or BGF. It's also in the slide in the second term where you multiply B to FG, right? So basically, even if you start from the third column and do the cofactor expansion, you still get the same answer for the determinant. So the thing is that this is a very easier way to calculate the determinant. And the good thing about this is that you don't need to worry too much about which row you start or column you start. As long as you do the answers and calculations correctly, you're going to get the same answer to the determinant. All right. Did I solve this? Oh, okay. So I'm going to give you some example for calculating this determinant like with real numbers. Okay. All right. Okay. In the example, we have a matrix where it's 1, 2, 3, and 0, 4, 5, and 106. So for this matrices, we're doing the determinant. And even if you sort the answer, I will really urge you to try to solve this. Like instead of starting from the top row, maybe some other rows like columns or third columns or I don't know, second rows. It's also possible. Try it and see if your answer is same with the determinant here. And after a few minutes, I'll tell you how this how this happens, okay? Let me give you some few minutes to solve this, okay? I'm going to assume you solved it because today we're just doing video recording. So for the determinant, we did exactly that. So let me tell you how we did it. So we can kind of see we also did the cofactor expansion for the top row, right? So basically we're doing for 1, 2, 3. So first we have do the cofactor for 1. So we choose 1 and we do the 2 by 2 determinant for 506, right? So you multiply 6 and 4 and divide it by... I think there's a bit of a typo here. Let me check. Right? Okay, I'm going to have to do it again, okay? So there's a bit of a typo, so I'm just going to solve it myself, right? Okay. So 1, 2, 3, 0, 4, 5, 106. Alright. We're doing the cofactor expansion to get the determinant for the first row. Right? So if we focus on 1, and we do 2 by 2 matrices, which is on here. So we multiply 1 with 6 times 4 is 24, minus 0. It should be 0, I think. There's a typo. I think it should be 0, not 5. It's a mistake, sorry. And for the second part, you first subtract them and you multiply 2. And now you do the matrix for here, which is 0 minus 5, okay? Alright, so you do that, and then lastly, you do it for the 3. So we have 3 matrix and again we do determinant here. It's going to be 0 minus 4, right? So 0 minus 4. So the answer is going to be 24, 10. Right? 24, 10, that's minus 12, so we're going to have to get 22, right? Tell me if I'm wrong, okay? So the answer should be 22, I think. Alright. Okay. And just for exercise, let me try to do it for like some other columns or rows. Let's just do it for like the third row for fun. So we start from there now. The same 1. And we do 2 by 2 matrices for the 2, 3, 4, 5. We get 10 minus 12, right? And then we subtract it again for 0. But this kind of doesn't matter because 0 is not going to be anything, so right? So like, when you get 0, what you get is basically, let me see, 0. Alright, 1, 3, 1, 5. So it's like 5 minus 0, but it doesn't really matter, right? Because it's already 0. And the last thing you get 6, which is 6 here, and you get 4, right? 4 minus 0. So you have 24 here, and minus 2 here. So you add them up, you get 22. So it's the same as 4 and 1. Nothing to worry about. All right. All right. Oh, before we go to Kramer rule, you should have kind of realized that you kind of saw the part where the cofactor expansion can get easy if you choose the row or column that has more zeros, right? Because if we do cofactor expansion in the top row, there's no zero. So we have to calculate for every numbers, right? We have to calculate for 1, 2, 3, right? But if you had chosen instead the first column or the third row, there's 0 inside, right? So what does that mean is that actually we don't need to care about this part because everything it does is going to give me 0. So it's kind of easy when you're trying to do cofactor expansion. Like the rule of thumb or some tip is that try to choose some columns or row that has more zeros, because if there are a lot of zeros inside, you don't need to do much more computation than other rows or columns. Okay, that's like a nice tip. And from that tip, actually, there's a theorem or so-called a good way to reduce your time for computation is that, I'm just going to write it here, is that when you have an upper triangular matrix or lower, so if you have an upper or lower triangular matrices, the trace, oh sorry, not trace, but the determinant of that matrix, let's say it's matrix A, so this is A matrix, which is either upper or lower triangular matrices, and we say the determinant of A is actually just multiplication of all diagonal elements. So what does this mean? Right? So what does this mean? Okay. Let me talk about this. Okay. By using the example. Oh, sorry. Keeps moving. So, for example, a similar example, but let's assume that this matrix is upper triangular, so it's 0 here, 4, 5, 6, like this. All right? So, try to solve this part, and I told you, easy way to calculate the matrix cofactor expansion is to basically try to choose the row that has more zeros, right? So we'll be either going for the third row or the first column. But since I like to do cofactor expansion for smaller numbers, I'll go for the first column, okay? So we don't need to care about this second 0 and third 0 because anything we kind of do is going to all give us 0. So we don't need to think about this one, right? And what this gives us is that because this thing is upper triangular, 1 times 6 times 4 minus 0 times 5, right? So basically 0. So what you get is actually 1 times 6 times 4. And this is just multiplying the diagonal parts, right? So what this tells us is that if a matrix is an upper or lower triangular, what you're going to get is that you just multiply by diagonally, and what you get is going to be the determinant. So it's a lot easier if you try to solve for the determinant of upper or lower triangular matrix, right? And this also holds for diagonal matrices, obviously, because diagonal matrices is just a special type of upper triangular or lower triangular matrix, okay? Some tips. Move on. Now we'll talk about Cramer's rule. So, what is a Cramer's rule? Okay, so Cramer rules is a bit more easier way to sometimes solve a question, especially if you're solving like kind of questions like, remember like the question we talked about, like solving the questions where AX is B, where AX, B are all matrices, and suppose that, oh, let's not say X is a matrix. X is like a column vector, okay? It's going to be like sort of, let's say it's like this, x1, x6, x3, something like these sort of matrices. And what we're trying to do is we want to know the answer to the value of X, because value of X are usually like the variables that we want to know about, and A and B are usually like the constants given, right, for the equations. And there's a way to solve it, and one of the very nice ways to solve it is by using Kramer's rule. And Kramer's rule kind of holds as long as the determinant is not 0. So as long as the determinant of this A is non-zero, we can use Kramer's rule to find what the value of X is. And you can kind of see why, because I already told you that if the determinant A is 0, that means A does not have an inverse. So that means X is not going to have a unique solution, right? Because if A has an inverse, you can just multiply A inverse here, and you get X is A inverse B, remember? And that will give you like basically the answer to question, X, unique solution. So this must not happen. So in this case, A would not have a determinant that is non-zero, okay? So in that case, you can't use Kramer rule. But if the determinant is non-zero, which means that X does have a unique solution, we can try this thing called Kramer rule, which helps us find faster some of the elements in the X. So the equation is as follows. So I've written it on the slide. So basically for variable X, each variable xi can be found using this. Okay, so what does this mean? I'm sorry, I think it's more easier to understand B as like also like a column vector. So like example here, it would be something like x1, x2, x3, right? And you have like, let's just go for y1, y2, y3. And for this example, let's suppose that A is just like 3 by 3 matrices. So it's going to be something like, you guys can see it, A, B, C, D, E, F, G, H, I, okay? So what does the equation mean is that we can actually get xi by the formula where we divide determinant of ai by determinant of a. So what is determinant ai? Well, we already know what determinant of a is, right? It basically means that we're just doing determinant for this value matrix. But what about AI? What is determinant AI? So determinant AI is basically you do determinant also, but the matrix A now, the column I is replaced by matrix B. So for example, let's say you want to know about x1. X1 means that the I index is going to be 1. So in order to do this, if you want to know about x1, you have to do determinant, which is determinant A. You put it in the bottom. Oh, and just for your information, sometimes we denote like this sort of symbol where we put like an absolute value on the matrices, and we call this like determinant. So when you say determinant of something, you can either write like det, like we just wrote many times, or we can like put an absolute value onto this matrix, and this just means that this is like calculating the determinant of that matrix, okay? So we have a determinant A in the bottom, and on top we also have a determinant, but now the different thing is okay, can you see what's different? You can see that everything is same. It's almost similar to matrix A, except that the first column has now changed into the column here, column B, right? So the result, y1, y2, y3, goes inside the first column of the matrix. It swaps the place with the matrix A. And we find the determinant for that. And interestingly, when you divide these two determinants, you get the answer for xi. In this case, it's like x1, the first element, okay? And similarly, if you want to know about x2, you just, instead of changing the first column, you leave it there and change the second column, like y1, y2, y3, okay? Very interesting. I just wanted to briefly talk about like some geometric interpretation of this. Like, so what does like determinant doing like in geometric like graphical term? So it's not. I don't feel it's like it's that important, but I just wanted to give you like the overall picture of what is happening in a graphical term. So in 2D, so that's like 2x2 matrices case. What determinant does is that determinant basically is giving the area scale factor when transforming a shape. So basically, when we're transforming some sort of shape in two-dimensional world, the determinant kind of gives the area for that factor, okay? Basically, okay? On the other end, 3D, what it does is that it determines the volume scale factor of a parallel pipe. So it's kind of like this. So basically, what it does is that in two-dimensional world, you have like some sort of parallelogram, and what the determinant kind of is doing is like is giving the area of the parallelogram. And for three-dimensional, of course, you have like one point up here. It's like some sort of a. I'm not good at drawing. So basically, what it's doing is like giving you the area of a parallel pipe, like kind of like a rectangular shape, except that the lines are all parallel to each other. Okay, that's like what we call the parallel pipe. Okay, so we're like kind of getting the area for what these matrices represent. So just remember this. It's like a graphical representation, right? And of course, like the sign of the determinant indicates like orientation. So like if it's positive, if the answer of the determinant is positive, it means it has like the same orientation. But if it's negative, it will have like a opposite orientation. Okay. So when is this important though? That's like one of the hardest questions. Okay. So when is it important? Well, we'll talk about this in the next session. But it's used in finding like the eigenvalue or eigenvectors. But we'll later talk about this. So we're not going to talk about this too much in detail. But it's used in finding eigenvalue or eigenvectors. Okay? Which are also very important concept in linear algebra. And secondly, we also sometimes use them to show that the matrix is invertible. Because we already showed that, remember like when we had the equation where A is B, we said that if determinant is non-zero, this means that the A has inverse. And if A has inverse, we can multiply inverse on the both sides to get the unique solution for X. And if the determinant of A is 0, this means that X does not have a unique solution, right? It's like, so if you check the determinant, we can kind of show if the X has a solution that's unique. So if a matrix A has a determinant such that determinant A is non-zero, this means that the matrix has an inverse. But the problem is, and it's also important that whether a matrix has an inverse, it's very important finding unique solutions. But note that it's not that actually efficient in solving problems with multiple equations, because you can kind of realize that, I mean, if you're using computers, fine, but for example, think about this, I mean, 2x2 matrices are okay? Just calculate determinants, maybe even 3x3, right? Even though there are like a lot more variables, we still kind of can do it. But in a lot of the situations, a lot of the kind of questions and multiple equations, there are like tons of equations that would mean like there's like an n by n matrices that you have to solve for a determinant. And you're, imagine doing a cofactor expansion for this, and it's going to be very painful, right? It's excruciating. So you can kind of realize that doing determinant for like, doing determinant for like multiple equations is not really a good idea for solving problems, right? In fact, just for solving problems, actually, like the Gaussian elimination method we just learned in previous sessions, those might be a better choice when you want to just get the answer for some problems in most of the cases, because sometimes it takes more time to calculate the determinant than calculating the answer using Gaussian elimination method and back substitution. So when you're solving like questions, it's a lot better just to try Gaussian elimination if you're just like wondering about the numbers, like the answers. Like mostly use determinant for other areas like eigenvalues and eigenvectors. I think that's the way people use it more often there. All right. I'm going to give you some exercises, and after this session ends, in the next session, I'm going to briefly talk about the answer to the exercise, and then we'll go on to the next session. Okay, we'll stop here for a minute.